Hello, everyone. In this video, we're going to continue section 8.4. We're going to look at our final theorem in this section called the absolute convergence theorem. So let's go through what this theorem says, and then we're going to use it in example 4. So this theorem says that if a series, that is the sum from n equals 1 to infinity of the absolute value of a sub n converges. So if we somehow know this series converges, then the series of just the terms without absolute value also converges. So notice how this first statement here about the sum or the series of absolute values converging is a more strict requirement than the sum of just the ANs converging. And why is that? Well, the ANs could be negative, right? So we could have some negative values in here. So as we add up numbers in our sum, if they're all absolute valued, so if they're all positive, then having some of the numbers be negative isn't going to hurt us too bad, since we know that the positive values all converge. Notice how the reverse of this statement is for sure not true. So I'm going to make that claim here, and we're going to justify it. So a big notice, or a big note before we get into the example, the reverse is not true. Meaning if AN converges, then we do not know that the absolute values converge. And this we can prove with an example. So we can actually see example 1 above. So we saw that the sum of the negative from n equals 1 to infinity of negative 1 to the n minus 1 over n, that converges. But if we look at the absolute values, so the sum equals a sum of n equals 1 to infinity of absolute value, negative 1 to the n minus 1 over n, which is equal to the sum of 1 over n equals 1 to infinity. This, we know, does not converge by the p-series test. This is a p-series with p equals 1. But the series with the negative does converge. And we saw that in example 1. Okay, so just a note there. So if the absolute values do converge, so if we know they converge, then the summation without the absolute values also converges. So let's take a look at this in example 4. So example 4 says, does the series from n equals 1 to infinity of negative 1 to the n over n squared converge? Justify your answer. So let's start off with some scratch work. So I want to use the theorem that we just met, this absolute convergence theorem. So I want to consider the series of absolute values. So for us, that would be the sum equals n from n equals 1 to infinity of the absolute value of negative 1 to the n over n squared. So notice what that series looks like. So we get then, when n equals 1, we have negative 1 to the 1, which is just negative 1, over 1 squared, which is just 1, absolute value, plus when n equals 2, that numerator becomes negative 1 squared, so we just get 1 in the numerator, over 2 squared, which is 4, plus then our next term would be when n equals 3, we have negative 1 cubed, which would just be negative 1, over 3 squared, which would be 9, plus we can just do a couple more of these, negative 1 to the 4th power would be 1, over 4 squared would be 16. We can see that we would alternate like this. Now we'd have negative 1 over 25, then positive 1 over 36, etc. Dot, dot, dot. Okay, so we can see that this then is just the series 1 plus 1 over 4, using absolute value, 1 over 9, plus 1 over 16, dot, dot, dot. So what we're doing here is we just have a series, n equals 1 to infinity of 1 over n squared. And maybe you saw that right away when I wrote this absolute value of the terms. What's going on here? The denominator is always positive. The numerator rotates between negative 1 and positive 1. So when we take the absolute value, we're just going to get this series here. Okay, well, does this series look familiar? Well, this is a p series with p equal to what? P is equal to 2 here. So this converges by the p theory test. P series, not theory, P series test. Cool. So that's the way we're going to prove this. And we want to justify our answer, so we want to justify it in a proof. So just to kind of talk through what that would mean. So what we're going to do is look at this absolute value theorem series, or the absolute series, we could say, show that it converges using that P series test. And then using this absolute convergence theorem, since the absolute values of the terms converge, or the sum of the absolute values of the series converge rather, then that theorem tells us that the series itself converges. So let's write that out. Proof. Since the sum of n equals 1 to infinity of the absolute value of negative 1 to the n over n squared equals the sum of n equals 1 to infinity of 1 over n squared is a convergent series, and specifically P series, with P equal to, then the series without the absolute value, so that's sum of n equals 1 to infinity of negative 1 to the n over n squared, converges. Why? By the absolute convergence test. Done. So we can just ensure that we have everything we need for a proof. Have we written complete sentences? Yes. Have we stated the theorem that we're using? Absolute convergence theorem. To show what? To show convergence. Why were we allowed to use that? Well, because we looked at that absolute value series, showed that it converged using a p test. So we're always, or p series test. So we're always justifying each of our claims with the test or theorem that we're using. And then we can conclude our final result that our series converges. All right, awesome job going through this absolute convergence test.